Somewhere, inside a lab colder than outer space, two tiny objects are quietly vibrating. They're not much to look at, circular, flat, metallic, about the size of a human hair. You might think they were part of a watch or a microchip, but what they're doing is something no watch and no machine has ever done before. These are not just objects. These are instruments, specifically aluminum drumheads, ultra-thin membranes precisely 20 micrometers wide, suspended on a chip. Sitting inside a cryogenic chamber, they've been cooled to just a fraction of a degree above absolute zero. Why? Because when things get this cold, something strange happens. The everyday world begins to vanish, and the quantum world starts to emerge. At these temperatures, even the tiniest bit of heat, a stray photon, a whisper of noise, can disturb an experiment. But these researchers weren't just interested in controlling noise. They were aiming to challenge something far more fundamental, the very limits of what can be known. And this is where the real story begins. For decades, physicists have lived by a rule. It's one of the foundations of quantum mechanics. It's called the Heisenberg uncertainty principle. And it says that no matter how good your instruments are, you can never know both the exact position and the exact momentum of a particle at the same time. The more clearly you try to measure where something is, the fuzzier its motion becomes. The more precisely you track its movement, the more its position slips into uncertainty. It's not a flaw in our technology. It's a law written into the fabric of reality. Until now, that law had never been seriously challenged. But at Aalto University in Finland, in collaboration with the University of New South Wales in Australia, a group of physicists asked a daring question. What if we could outmaneuver uncertainty itself? Not by breaking the rule, but by stepping outside of its reach. They began with those two tiny drums, but they didn't treat them as separate instruments. Using a technique called microwave cavity optomechanics, they linked the vibrations of both drums to a shared electromagnetic field inside a superconducting microwave cavity. As energy moved through the field, it caused the drumheads to oscillate. Then came the leap, entanglement. Through careful tuning, the team caused the two drumheads to become quantum entangled, meaning their properties became deeply interwoven. Even though they were physically distinct, they behaved as if they were part of a single, unified system. When one drumhead moved ever so slightly in one direction, the other responded in the opposite direction, instantaneously and with perfect symmetry. This phenomenon, once called spooky action at a distance by Einstein, was now unfolding not in a photon or an electron, but in objects big enough to be seen under a microscope. But the goal wasn't just to observe entanglement. The researchers were constructing something far more exotic, a quantum mechanics-free subsystem, or QMFS. What does that mean? It means they arranged the system so that certain combinations of the drum's positions and momenta, called collective quadratures, could be measured with almost no quantum backaction. In other words, they could simultaneously track position-like and momentum-like observables without triggering the uncertainty trade-off that usually scrambles one when you measure the other. This isn't science fiction. It's real, peer-reviewed physics, published in Science in 2021. The uncertainty principle still holds for individual components. But by treating the pair as one entangled quantum system, the researchers created a clever workaround. The noise, the quantum uncertainty, didn't vanish. It just got redirected into degrees of freedom they weren't measuring. It was like tiptoeing through a minefield by knowing exactly where the mines were and simply walking around them. This changes everything. It means that, in the right configuration, quantum systems can give up more of their secrets than we thought. And this could unlock a whole new generation of tools. Ultra-sensitive quantum sensors, enhanced gravitational wave detectors, quantum computers that operate with more precision and less error, and even clocks that measure time with a stability we've never seen before. All of it made possible by two tiny aluminum drums, colder than the void of space, vibrating together in silence, rewriting the boundaries of what we're allowed to know. And that's the part no one saw coming.